All right, welcome to day 4. Today we're going to be learning about the washers method. Tomorrow will maybe be, or next class will maybe be the dryers method. That was a pause for laughter. Uh, so today's the washers method. You had the disk method for homework from last class. We're going to pause the video to let you check your answers for 2 minutes. In your planners, you can also be writing down just day 4 problems. Notice there's some on page 1. You got 2 more of the problems like we've been doing 2 each night, and then you got packet page 2 to do as well. So we'll pause for 2 minutes to check your answers. If you have something wrong, see if you can figure it out within your group, and we'll go over the answers quick after 2 minutes. All right, so we're going to go through each of them briefly. While we're doing this, the sub will be passing out the notes sheet for today. Also, you'll be getting your next problem set. Make sure you have your problem set out, the current one to be collected if you have not turned that in already. So both our pictures on the left, we're going over the x-axis, so we're doing disks. Your disk would look something like that. That's your radius, so we have pi times a radius squared, which is a vertical line coming up from the x-axis, which is a y value. But our thickness, if we were to slice this, the thickness would be a slice along the x-axis, so that's why we're dx. So we have pi times our y value squared, but in terms of x for each. And then we had our x values where our interval started and ended. Next ones, we're going around the y-axis, and our slices were going horizontally. So in both cases, we were going to have dy's. Our disks look something like that. So that's our radius. So we're just doing pi radius squared, where our radius is an x value because it's coming out horizontally from the y-axis. So notice in 8, we had to get x by itself, so we squared both sides. Added the x squared over, subtracted the y squared, took the square root. Okay, so both of them we had pi times that x value squared, which is the radius squared dy. Did it out, subbed everything in. They gave you the function. We are bound by x equals 0 and x equals 3 and y equals 0, meaning we had this space here that we were spinning around the x-axis. So that would just create a disk with our radius being a y value in terms of x. And a similar idea in 26. So here's the rest of the work for that. So we had a little u substitution that we had to do in the left-hand one, and an additional u substitution in the right-hand one. All right, 32 was the challenge one. So this was our region here, and we spun around the y-axis. Well, this was one edge, that created that, but then the inner edge is going to create its own circle of hollowness. And that's what creates the washer shape, which is what we're going to look at today. So that's why this was a challenge one. We haven't actually learned this yet, but you actually had the circle for the outer edge there, then you had to subtract off the circle gap that is essentially created by that line x equals 2 as it goes around. So that's what we have in the setup there. We have pi, and then we have a radius squared for the outer, and then minus a radius squared for the inner. Really, they each have a pi, but we've just factored that pi from the pi r squared out. And our x values of our bounded region, or sorry, our y values of our bounded region go from 0 to 5. We're in terms of y's because our slices were horizontal, making it a dy. All All right, 47, we had a Formula 1, kind of like we saw in the notes. So we want to show that the volume of the sphere is 4/3 pi r cubed. So we're going to use the top half of a circle as our equation, and we'll spin it around the x-axis. So that's x squared plus y squared equals r squared. Because we're going around the x-axis, our disks would look like that, making our radius be a vertical line, which is a y value. So get y by itself, and you get square root of r squared minus x squared. So we'll do pi times that squared dx. And our bounds for those slices, we go the furthest left is negative r, furthest right positive r. So after you square it, the radical goes away, and it's important to keep in mind we're taking the antiderivative with respect to x. So r squared is actually a constant. So we get r squared x minus 1/3 x cubed. Fill in the r and the negative r and neaten it up, and it actually gives us that 4/3 pi r cubed. And then the 3a and 3b, we had the bottom equaling u, make a little adjustment so that we could just do the natural log. And then the other one, that was really e to the x being squared in the bottom, so we could do a u being just e to the x, which led to an arctan. All right, so today's lesson, we are using washers. So discs were basically a circle with a little bit of thickness. The little bit of thickness was the dy or dx. Washers are created when the region we are spinning around is not completely resting against what we are spinning around. So just to see a little picture of that on the homework, like these ones, the region was completely resting against the x-axis, which is what we are spinning around. But in the challenge one, our region was not completely resting against the y-axis, which is what we were spinning around. And that is what created the washer shape. So whenever your region is not resting against what you are rotating around, that creates a washer. So you should have your notes packet, hopefully at this point. So if we wanted to find an area of this washer, we have an outer circle. Let's call this, let's do the inner circle first. We'll call the inner circle's radius r1. We'll call the outer circle's radius r2. So therefore, the area, notice area, 2 dimensions, would be pi times the r2 squared minus pi times the r1 squared. Is outer circle minus inner circle. Now the volume of this solid, essentially we have a cylinder with a cylinder chopped out of the middle. Think of like the combos snacks. Hollowed out middle, but if there's no stuff filled into these. That's kind of like what we have here when we have our washers. So if we wanted to find the volume, we would just have to throw a height in there. So we would have pi r squared, r2 squared times height minus pi r1 squared times height. Now for us, the height of this cylinder is going to be the little bit of thickness we have from our slices. So that little bit of thickness will be our dx or our dy. So the height will be a dx or a dy. Let's just say hypothetically it's a dx. The pi will be able to pull out in front of the integral, and we'll just be left with the r2 squared minus the r1 squared. So essentially a washer's, your setup is the pi times the integral of the outer radius squared minus the inner radius squared, and then d whatever we have. Dx if we're doing vertical slices because we're slicing the x-axis, dy if we're doing horizontal slices because we're slicing the y-axis. All right, so if we want to, for this, our region bound by x squared and square root of x is revolved around the x-axis. So x squared will look something like this. Square root of x will look something like that. So the region we're looking for is right here. So today's a washers day. We know we're going to do washers. But on like a test, we would want to see, oh, that region is not completely resting against the x-axis. That's how we know we're going to do washers. Because from the outer edge, when we spin it around the x-axis, it'll look something like this. And the inner edge, when it spins around the x-axis, it'll look like that. And then that blue space basically becomes that. So that's what creates the washer shape. So our slices, you're always slicing with washers and discs perpendicular to what you're rotating around. So our slices, we are doing this way. That's going to slice the x-axis, so we're going to have a dx. We're going to have a pi. And then our integral, we're going to have the outer radius squared minus the inner radius squared. Well, our outer radius would be, well, how far is this from the x-axis? Well, that's just a vertical line coming from the x-axis. That's a y value, or it's just our function value of square root of x. So we'll have that squared minus our inner radius squared, which would be like that distance, which is just the y value for the x squared function, but we need it in terms of x, so it's x squared squared. Now our x's go from 0, and then we intersect again at x equals 1. So we're from 0 to 1. And we're going to pause the video for 3 minutes to allow you to do this out and do the integral. Okay, square them both. You got x minus x to the fourth. Antiderivatives. Evaluate at 1 and 0. Get a common denominator, bring it together. We should get 3 pi over 10. All right, moving to the back, we've got x squared, and we have 2x. So x squared is going through points like 1, 1, 2, 4, 0, 0, negative 1, 1, and negative 2, 4. And y equals 2 to the x, or 2x, sorry, not 2 to the x. We're going through like 1, 2, 2, 4. The graph looks something like that. So that space in between is our bounded region. Okay, bounded means completely surrounded. We're going to spin this around the y-axis. So first thing we want to notice is this region is not completely resting against the y-axis. So therefore, it's going to create a washer shape when we spin it around. Because it gives, because it's going right to left there, our slices will be horizontal, and we'll be using dy. So we'll have pi times some radius squared minus some radius squared. So our outer radius goes from what we're rotating around to the outer edge. It's a horizontal line coming from the x-axis, or from the y-axis. That's always called an x. But x in terms of y for that parabola would be square root of y. The inner radius would go from here to here. That's also an x, but an x for our line. So x would equal 1/2 y. On our integral, we got to make sure we're working with y values. The y values in our region go from 0 to 4. And we're going to pause for 3 minutes to let you do out this integral. All right, so when we square them, we should get y minus 1/4 y squared. Do the antiderivative. Evaluate at 4, and you get 8 and minus 16 thirds. Evaluate at 0, you get 0 for each. Common denominator, bring it together, you get 8 pi over 3. All right, so we want to graph cos x, sin x, and x equals 0 and see where they create a bounded section in the first quadrant. Well, here is x equals 0, so that needs to be one of the walls. There's roughly sine. There's roughly cos. So in the first quadrant, we need a section that is walled by all 3 of those things. That section would be right here. So that's the region that we are spinning around the x-axis. We want to recognize it is not totally resting against the x-axis, so this is a washers. Okay, we would get this here. So we're going to have pi, the integral. We're going to have some radius squared for the outer minus some radius squared for the inner. Now we're always slicing it perpendicular to what we're rotating around. So we are slicing these vertically. When you slice vertically, you're cutting the x-axis. So this would be a dx. Now our x values start at 0. And then we got to think, where's that first time that sine and cos are equal to one another? So if you think of your special right triangles, that is happening at pi over 4. Now when we have our washer, the outer radius should go to the far edge, so it starts where we're rotating around to the far edge. So that's going to hit our cosine function. So we'll have cos squared x. Our inner radius, the inner edge, okay, right here, that is our sine function. And then we're going to pause the video for 1 minute. Cos squared x minus sine squared x is an identity. We're going to see if you can remember that from pre-calc. So we'll pause for 1 minute for you to see if you can come up with it. So hopefully somebody out of the room was able to come up with cos 2x. That's our double angle for cos. So because of that, now we can do this antiderivative. We can do a little u substitution. So we'll let u equal 2x. Du will equal 2 dx. Our leftover is just dx, so we got to correct by a half. So we are going to have pi. Our integral values switch for our u. We've got to double each of those x's to get our u values. So we'll get 0, and we'll get pi over 2. This will become cos of u du. Antiderivative of cos, just sine u. And we're going to evaluate from 0 to pi over 2. Oh, you know what? I forgot to put the 1/2 out front here from our du. So we're going to have 1/2 pi. Sine of pi over 2 is 1, minus sine of 0 is 0. So the volume that we get when that region is spun around the x-axis is 1/2 pi. And you can say units cubed if you want. Again, on the free responses for this on the AP, they don't tend to have the units as part of the scored part. All right, so that's it for the video. You can work on your homework with any remaining time in class, or you could work on your new problem set.